Okay, let's see here. We are recording. Good. Okay, so picking up where we left off last time. So we finished chapter 2. Took us a while, but we got there. Moving on with chapter 3. Now we've already covered section 3.1, moving along to 3.2. We're going to talk about arc length. There's a bunch of cool things to talk about in this section that don't really quite make the cut of what's important for us to spend time on. So some of this I'm going to spend a lot of time on, and some of this I'm going to cut through pretty quickly. So what is important is this business right here. A lot of what's in here we're going to be using extensively in various different parts of the course. So let me talk about what we're doing here. The question that segues best into this is how do we find the length of a parametric curve? Right? How much ink would it take for me to trace out that curve on a piece of paper, for example? Or how long would it take to walk on that path, that kind of thing? The idea is that if you have a curve, there's your parametric curve, and if you want to focus, though, on just one little piece of it, that I'm going to call, there's that little piece of curve. There's various things that you can say about that little piece of curve. The very first one I want to talk about is what is this dx vector that I've drawn right in here. And this is exactly what it looks like. D meaning differential. This is our linear estimate of how much the function changes, right? I mean, that's what differentials are. They're linear estimates of how much the function changes. Keep in mind, the function gives you position. So this is our linear estimate of how much our position has changed. It's our linear estimate of our displacement. So sometimes I'll call this the displacement differential. Very often I'll just call it the vector differential or the position differential. So that dx, I think, is pretty believably x prime dt. This is a callback to a standard formula of either physics or geometry. Take your pick. Position is velocity times time. Right? I think that's very intuitive. Recalling that, of course, the derivative is the velocity, and so these are basically saying exactly the same thing. Okay, now the next thing I want to talk about is the length of the little piece of curve itself. So not how much does my position change, but how much did my odometer click up as I drove on that piece of road, right? The actual length of it. The huge difference between ds and dx. Dx is a vector. It's a change in position, which is a vector. Right? ds is a scalar quantity, right? It's just a measurement of distance. And basically ds says how much, as you move over that little piece of curve, how much has your total distance traveled increased. So the big idea here, what I hope is an easy pitch, is that dx is the magnitude of the dx vector. Right, and I think the picture makes that pretty believable, right? Another way to say it is that our linear estimate of distance should be the magnitude of our linear estimate of displacement, right? If you think about what a displacement really is, a displacement is, there's a direction involved, and the other aspect of a displacement is how far did you go in that direction, namely a distance, right? So that's one of the really big ideas here, that ds is the magnitude of dx. Okay, all right. So the third object that I want to talk about here is I'm going to call capital T, and this is somewhat standard. This is a very common choice anyway, capital T. It is the unit vector pointing in the direction that the curve is going. Now, you can think of this in a couple of different ways. You can think of this as the unit vector pointing in the direction of dx. You can think of it as the unit vector pointing in the direction of the velocity. They're the same direction. Right? So take your pick. You'll notice that the formula that I've written down here is unit vector in the direction of the velocity. And, of course, again, that's the exact same thing, whether you think about it in terms of differentials or not. Okay. Also going to be an important quantity of interest. Everybody on board so far? One last little thing before we go on. One last unusual thing from this picture. Okay, so the last thing I want to talk about is looking at the dx vector. We've talked about why these things are equal, I should say. So what about this right here, right? Why is that thing equal to these other things, right? Why is this also dx? And again, there's kind of different ways to think about it. One way to think about it is just kind of brute force directly. I mean, dx represents, this is a vector that points in the direction that you're going and represents how far you've gone in that direction. And pretty literally, that's what this says, right? T is the unit vector representing the direction you're going, and ds is how far you've gone in that direction. That's what a displacement is. Right, if you're so inclined. And here's another way to think about it. And if you're less intuitive and more sort of interested in formulas, I'll point out that if you take this formula for t that we've already agreed to, and if you take this formula for ds that we've agreed to, then notice this product t ds boils down to a product here where the magnitude of v's in the denominator there, it's in the numerator there, those magnitude of v's cancel, right? And you get v dt, which we've already agreed is dx. So, different way of thinking about it. Take your pick. Okay. Alrighty, so that's really the most important part of this section. But let's go ahead and answer the question that we came here for, namely how to compute the length of the parametric curve. The length of the parametric curve, I make the observation that if you have a parametric curve like this, then the total length is the sum of all of these little bitty pieces of length that you might chop it up into. Right, now this is a callback to what you all know about integrals. By the way, of course, we're going to be talking a lot about multivariable integrals in this class. But the big picture takeaway of integrals is that it allows you to chop up a hard question into little pieces and just add up the little pieces. And that's all I'm doing here. So we have a formula here for what ds is. The length of that little piece of parametric curve, take your pick, right? We've got a bunch of options. And this just says, yeah, I'm just going to add those up over the entire curve. So I'm going to use this formula right here. Oh, I missed. V dt to represent that ds. And lo and behold, check it out, we have ourselves an integral that we can just crank out. And so no big deal. Here's an example. I'm going to compute the length of this parametric curve for that range of values of t. And by the way, now to you might say the first question we should ask, what does this parametric curve look like? Right? It's always satisfying when you can get a good answer to that question. It's not an immediately obvious question of how to answer, and it's also entirely unnecessary. We really don't need to know what this thing looks like. So what we're going to do is just plug right into our formula. You want to compute the length of a parametric curve. Length is that formula, which I write down there. Notice all I had to do was compute the velocity, right? The velocity is what I've got in here. That's the derivative. That's what you get when you take the derivative of position. Right? Derivative of position is velocity. And then you end up with, of course, if you compute this magnitude, whoops, I'm mixing my colors. If you compute that magnitude, it's the square root of the sum of the squares of the coordinates. And you find yourself with an integral to compute. And sadly, this one worked out to be a hard integral, right? I don't really want to have to deal with that integral. But that's the integral you'd have to compute this length. And by the way, unfortunately, very often you end up with ugly integrals. And you can see why without too much trouble. You're looking at an integral of a magnitude. Magnitudes are square roots. Square roots make for ugly integrals, right? It's as simple as that. Is everybody with me? Everybody happy? Okay. All right. All right. So, all right. Next thing I want to talk about is called an arc length parameterization. This is another very, mathematically important topic that I would love to be able to spend a bunch of time on, and it, in terms of how important is it to the rest of the material and to your future careers, that's another one of these things that doesn't quite make the cut in terms of something that we're going to spend a lot of time on. So I'm going to, for the rest of this discussion, the next page and a half, basically, I'm going to be kind of hitting highlights. I want you to be exposed to this idea. I want you to see how to do it, but we don't need to agonize over the details here. So first observation I'll make is that curves have many parameterizations. Parameterizations are not unique, right? We've seen this with lines. You can start at kind of whatever point you want. You can move with, there's various different tangent vectors to that line, right, that tell you what direction you're going, and take your pick, right? So lots of different parameterizations. Now here is a different kind of reparameterization. Y'all will recognize the graph parameterization of that curve. Arguably the easiest parameterization to write down, boom, immediately. Okay. And I'm going to make the observation that I can create a new parameterization just by taking my t and just making up some other expression of some other variable. It doesn't hardly matter what even you pick. I mean, there's some little details we'd have to worry about. I don't want to worry about it. But just renaming t with some other expression. Notice this t just does exactly what it's supposed to. Notice that this t does exactly what it's supposed to. And the result then is that this is a different parameterization for the same exact curve. And it might not look like it. You might think, wait a minute, no, because I started with a quadratic, and this is like cubic and stuff, right, at a casual glance. But notice, this totally works. Totally works, because after all, this y here is indeed the square of this x right here. Y is x squared. So this is tracing out the exact same curve. Totally different parameterization. Is everybody with me? Kind of a weird thing to want to do. I took something simple and I made it harder. Why would I ever want to do such a thing? The big idea is you can, and again, if you have an algebraic relationship between two parameters, you can solve for one, plug it into the other, and you can reparameterize however you might want to. The slick move here is to do what we call a parameterization where your new parameter is arc length itself. That's the big idea. So I'll point out we have a formula for arc length, right? If you have parameterized with respect to t, and if t gets you to a particular point on your curve, and let's suppose that you've got some starting point set that's nailed down. We're gonna leave that fixed. That's where t equals 0. Yeah. We can just straight up write down a formula for how long the curve is, the arc length. Here's our formula. That's on the previous page. Integral of velocity. Well, integral of the magnitude of velocity. Integral of speed, you might say. And this is a formula. And check it out. It gives s as a function of t. I have now a relationship between two parameters. Time as I drive along this road, for example, and distance traveled as I drive along this road. So, by the way, you can actually experience this in real life. You can, as you drive along some road, you go on some road trip, right? And wherever you might happen to be, you can look at your watch and see what time it is, right? You can also, as you drive along the road, look for mile markers. on the side of the road, right? And those mile markers tell you literally how much distance have you traveled along the road from some preset, starting point, mile marker 0, and how the state does that depends on, that's their thing. It doesn't matter. Okay. So this is how you would algebraically do that. There is an aspect of this I want to address. A lot of students get weirded out because I've used a different letter here, even worse, a Greek letter, right, as my dummy variable for the integral. How come I'm using this weird, scary-looking dummy variable instead of just t? Why didn't I just call it t like we did on the previous page? It's much more comfortable and familiar and easier to draw. I mean, that's a weird little character, right? So why with the tau? And the answer is t has already been used. T is representing the time at which I'm computing the corresponding distance. So I can't have t represent the endpoint of my time interval and also have it represent every value in between as well. You just can't do that, right? That's confusion of variables. It doesn't make any sense. So ultimately, the point here is don't worry about this tau. It's just something that we have to rewrite as tau just for sort of formality purposes. It's nothing to sweat. Okay. So just like on the previous page then, once you have an algebraic relationship, which we now do, right, then you can just plug the one into the other and reparameterize. In particular, take your existing parameterization, right? Notice that, well, here, let me do it like this. Take your existing parameterization and solve for t as a function of s, and plug that in, and out comes a new parameterization where you have position ultimately as a function of distance. So why would anyone ever want to do such a thing? And here's where I'm going to be quick about it. And again, I don't want to get bogged down in details. My goal here is to expose you to these ideas, and so that you know that they're there. But we're not really going to do much with them. There is a homework exercise where you have to crank one of these out. Nothing to worry about. So one thing that's natural about an arc length parameterization is it's intrinsic to the curve. And you all may recall I talked before about the difference between the road and the road trip, right? And if you suppose I'm going to go up to the mountains over Fall Break, for example, and so when I drive that path, right, I can talk about the experience that I will have as we drive along that road, and that's gives me position as a function of time, but that's really kind of my deal, right? That's my experience. That's my road trip. But you can also talk about from my house to the mountains. What is where is the road per distance from my house? And that's settled. That doesn't depend on how fast I drive, right? It doesn't matter if I start a couple hours late, or if we decide to wake up the next morning and go, right? That's something that's intrinsic to the curve. Where the road is, 15 miles away from my house, is settled. It's intrinsic to the road itself. So that's a good thing. And when you're doing math, you want to avoid arbitrariness if possible. And this is a way to do that. This is naturally intrinsic to the curve. The other nice observation to make is that it is a unit speed parameterization, and this has mathematical advantages. Y'all will recall, of course, the single variable chain rule. Right? This is vector valued, but it's still single variable. Right? So the chain rule is exactly kind of what you would sort of expect. No fancy multiple intermediate variables kind of a situation. And then take the magnitude of both sides and notice that these two things are the same. They both represent speed. This says magnitude of the velocity vector. That says distance per unit time. They're both speed. So those things being the same, that tells me, as I had claimed, that this is 1. And so therefore, if I look at the arc length parameterization, position is a function of s, the derivative of that parameterization with respect to s, of course, that's the parameter, is 1. Okay. All right. Okay, bad news. Very hard to compute the arc length parameterization. I'm going to let you all read this example. There's some nice kind of algebraic and trickery in this example, and even still, it ends up being kind of intractable. And I just want to hit the highlights of this. I've gone to some trouble to find a parametric curve that allows for the nastiness of the square root that comes from magnitudes to be canceled out by what's inside being a perfect square. Now that's a little bit of a tricky move, and you can trace it back and see how I did it. It's not really a mystery. But even with that, which in practice most of the time doesn't work out, most of the time you're what's under the radical is not going to be a perfect square, and you're going to have an integration nightmare. Even when I've dealt with that by being tricky, it remains that my relationship between s and t is something that I can't solve. So I can't solve for t here algebraically. And so if I were to try to do an arc length parameterization of this curve, again, despite my tricky efforts, still can't write it down algebraically. So that's too bad, but it's the nature of the beast. Is everybody okay? All right. Okay, so new object that we're going to talk about, something called a vector field. Really important in multivariable calculus, especially when we get to what I'm going to call here chapters 6 and 7, which outside of this course is very often called vector calculus. And vector calculus is tremendously important. I asked a professor in the engineering school one time, for those of you who are engineers, what's important to y'all? What do you most need students to know about multivariable calculus? And she said, well, vector calculus is number 1. Number 2, vector calculus. And number 3, vector calculus, right? So this is the emphasis that she put on why, what is it that you really need to get out of here with vector calculus. And one of the main objects of vector calculus is a vector field. So here we go. A vector field is just a function. It's a certain kind of function. In particular, the number of inputs and the number of outputs have to be the same. And when we say we're going to view this function as being a vector field, the implication is usually that we're going to view the input as being a point in Rn, in this case R2, and in this case over here R3. The input's going to be viewed as a point, and the output is going to be viewed as a vector. So, such as represented by that arrow in the 2-dimensional picture, or maybe this arrow in this 3-dimensional example. Okay, so that's all it is. A function that we draw in this weird way where the input is represented as a point, the output is represented as a vector, and in particular you'll notice, and this is also part of how we view vector fields, the arrow that we draw representing that output vector has its tail at the point that was the input point that led to that output. Is that cool? Everybody happy? I guess I'll point out while we're here, notice that this is yet another different kind of picture that we're drawing to represent a function. Now, y'all remember that whole thing, right? It was beyond a spiel. It was an actual thing, right? Where I made this big distinction between a graph versus a level set versus when we draw parametric curves, we're drawing images. Those are three totally different kinds of pictures that each have their own totally different calculus because they're totally different in how they represent a function. Completely different constructions, right? This is different from all of them. This is not a graph. This is not a level set. This is not a parameterization. Totally different, right? And we're going to find that the calculus of vector fields, again, by which I mean when we start writing down different kinds of ways that I can construct derivative-like things that involve these kinds of functions, what do they look like in this picture, right? The calculus of vector fields is going to be a really big deal. And what we're going to do in the next section, 3.4, is we're going to preview a little bit of that. Now, most of the calculus of vector fields is going to be, well, that's kind of what vector calculus is about. Full discussion of that will come much later in this course. But a little bit of a preview in 3.4, hopefully later today. Yeah?
What's the difference between a vector field and a slope field?
That's a great question. A slope field, at a point, you associate just a slope. So there's no magnitude. There's kind of a direction, but even if you think about it, if you have a slope field, it's not telling you if you're going that way or this way, right? So it's kind of got less information in the output that you associate to any given input point, but it has a lot in common. Absolutely, yeah, very, very. Thus the same use of the same word field. Yeah. Anybody else? Great question. All right. So yeah, just a couple of examples. Start with this constant vector field on the left. I say constant because you'll notice the output is constant. Doesn't depend on where you are. Right? So thus the term constant vector field. The weird thing about this is what it looks like. Notice it doesn't, it kind of looks like something's increasing, doesn't it? Right? But no, this is a constant vector field because at every x comma y, no matter which of these points you're looking at, you always get the same field vector. It's always 2, 1. Right? Thus constant. So, yeah, different from graphs in terms of how you interpret it. All right. Okay, let's see here. Here's another example here. Look at this one. This is also sort of a standard interesting thing. And notice at any given point x, y, keep in mind the input to be interpreted as a point. The output, what you might call the field vector, right? Notice that field vector, it's just the same. It's just x and y, which if I'm going to draw as a vector means I'm actually looking at the position vector for the point where I'm evaluating. So the field vector is literally the position vector for that input point, and I can represent that position vector. I can represent that position vector like this, but of course when we draw field vectors, we draw them so that the tail is at the point where we were evaluating. So that's what you get. So you get a vector field where at every point the field vector is pointing, you'll notice, away from the origin and with magnitude equal to the distance to the origin. And thus a picture kind of like this. Everybody kind of buy it? All right. Here's one. Also kind of interesting. Now I'm going to leave some of this as an exercise for y'all, but I will point out what the observation is to be made, and then I'm going to leave it to y'all to check the details. Notice that at any point, such as, for example, that one, and now keep in mind, this is perfect correspondence between points and vectors, right? So just because I can, I'm going to go ahead and represent that position by its position vector right there. So notice that my input point and my output vector, and the output vector I'm going to draw in the usual way right there, and then for my own, again, selfish purposes to make the observation I want to, I'm going to draw that exact same vector here. Right? Vectors don't have location. I can draw it anywhere I want. I have to draw it up here as part of the vector field, but I can draw it down here for my other purposes. And notice the observation then. If I look at these two, not interpreting the input as a point, but interpreting the input as a position vector, not interpreting the output as being an arrow at the point, but interpreting it as being the exact same vector represented by an arrow at the origin. Check it out. The green is just a 90-degree rotation counterclockwise of the purple. Right? So that's how you're going to get a handle on, what does this vector field look like? Well, this vector field is what takes x comma y and turns it into negative y comma x. And the exercise is for y'all to confirm that a quarter turn counterclockwise is what does that. And how are y'all going to do that? Well, you're going to remind yourselves that rotations are linear transformations. Right? Linear transformations are represented by matrices, and when you do that, the columns are the images of the standard basis vectors. So apply those ideas to a quarter turn counterclockwise, multiply that matrix times x comma y, and you're going to find that you'll get negative y comma x. All right, so now that's I think everyone should make sure that they become at least able to do that calculation. So if you get stuck, of course, come to my office hours. Very happy to help. Don't forget Professor Hughes' office hours. We have a TA office hours on the weekend and a couple of nights during the week. I forget which dates. But seek help if you need it. But hopefully y'all can do that part. Okay. All right, here's another important vector field. This is called a radial inverse square vector field, which seems weird when you look at this formula because you see that cube and you're like, wait a minute, why do they call it inverse square? Right? Well, the reason we call it inverse square is because in order to make sense out of the magnitude, you have to separate out a unit vector representing the direction before you can infer that what's left over is the magnitude, right? So this here, what I have in green, is the magnitude. And notice you needed to, one of these factors, one of these three factors of magnitude, one of them I had to pull out over here to turn this into a unit vector, right? And so even though you see a 3 in the denominator here, this is actually inverse square in magnitude. Is that cool? All right. Notice further that this part is a unit vector, but furthermore, it's a unit vector pointing to the position x. So it is a unit vector that wherever you are, the unit vector that's pointing radially outward from the origin. Is that okay? Is everybody happy with that? Okay. And so you get this picture. This vector field, interpreted like so, gives you a picture that looks like this. Now the picture that I've drawn here is where this factor c is negative. That's why the students get weirded out by this because the radial unit vectors are pointing outward, but with a negative c, the resulting field vectors would be pointing inward. And the reason I drew it like that is because I wanted to be able to relate this to what what I'm going to say is the most sort of day-to-day familiar example of this is that this is a gravitational field. Gravitational fields look like that, and they have these formulas right there, where c is negative, by the way. Gravity pulls down, not up. Thankfully, right? It'd be horrifying if it was the other way around. Okay. Now, of course, there's other examples of this, and as it turns out, by the way, electric fields also look just like this. And this is a really nice fact, by the way, that electric fields, which are extremely important, especially in engineering, especially in like ECE and stuff, right? But in all kinds of engineering, you have to understand electric fields. They're just unbelievably important, fundamentally important in engineering. And what we see from this is that if you want to develop some intuition about electric fields, just think gravitational fields, which are so relatable, right? Nobody can see an electric field, but we walk around all day, every day with some intuition for gravitational fields. So I think this is a really nice connection that these two things are related, even though they're completely different physical phenomena. Okay, how are we doing? Everybody on board? Cool. All right, some old news. Let's talk about gradients. Gradients, they always point uphill on the graph. We knew this. That's old. Let's see, when did we first see that? A couple of days ago, I guess it was. Maybe it was Friday. I can't remember if it was Friday or yesterday. But already established, gradients point uphill. The new observation I'm going to make here is that a gradient is actually a vector field. And we didn't think about it that way at the time, but check it out. It totally is. If you have some function like this, and if you compute the gradient, check out the formula. The formula is a vector. Right? At any given point x comma y, there is an associated field vector. In this case, the formula is this thing right here, 2x comma 2y. So input point, output vector. It's a vector field. So the reason we didn't notice this previously is because we were just considering one point at a time. We were only looking at, so for example, at that particular point. And we were thinking about what's happening on the surface above this particular point. And what was happening was that uphill, oh gosh, it's kind of hard to draw uphill here, but uphill would be kind of like that maybe. And this is the corresponding direction in the domain, on the map, if you will, that would have you, if you go in that direction on the map, that would have you actually going uphill in the bowl that is this graph. So we were just previously looking at one point at a time, and I'm just making the observation here that, well, yeah, but you can draw that field vector, right, for any number of points. At this point, you can draw that field vector, and at this point, you can draw its corresponding field vector, and likewise at all these other points, you can just draw their corresponding field vectors, and check it out, you get a vector field. And again, furthermore, check it out as we knew it would. These field vectors always tell you which way to go to get up on the graph. Okay. All right, so gradients are vector fields. By the way, real quick, it turns out that gradients are special vector fields, particularly special in some powerful ways that are way not obvious right now, but that we will see in great detail when we get into chapters 6 and 7. So for now, that's just a little bit of foreshadowing. I want to talk about the terminology a little bit. If we have some real valued function, we can take the gradient. We just got through talking about how the result is a vector field. So I think that it's reasonable to say, hey, look, what comes out of the gradient operator, shouldn't we call that the gradient of whatever function we're taking the gradient of, right? It's so obvious it's almost hard to say, right? Of course that should be called the gradient. Reasonable next question, though. If you have a vector field given to you and you want to ask, how would I describe the thing that when I plug it into the gradient operator gives me that vector field? How would I describe, given a vector field, what is the thing whose gradient is that vector field? And I think very reasonable is to call it the anti-gradient. And of course, I'm just stealing shamelessly from the sort of grammatical construction that y'all all saw in single variable calculus, derivative and antiderivative, right? I mean, they're very familiar old terms. I hope y'all remember derivative and antiderivative, right? Same thing here, gradient and anti-gradient. Seems pretty natural to me. So this is what you're going to hear me saying loads of. The function whose gradient is a given vector field that you're interested in, we will refer to as the anti-gradient of that vector field. Now, having made my case for why I think that's the right terminology, let me point out that there is a different terminology in much more common use, unfortunately. This thing, very often called a potential function. And the reason why is because if you're doing physics, then there is a gradient relationship between forces and the anti-gradient. The anti-gradient, y'all may remember this idea called potential energy, right? The gradient of potential energy relates to the force. Now, unfortunately, though, there's this minus sign to worry about. And I'm going to go ahead and highlight this minus sign in red here. And roughly speaking, the point is this. Forces pull downhill, gradients point uphill. That's all it is, right? And so because of this, because forces point in the direction you're going, which is toward lower potentials, but gradients always point toward higher potentials, you get this minus sign. So if you have a force given to you and you want to talk about what I would call the anti-gradient, you can see it connects to potential energy. You can see why they'd want to call this the potential function. But it's not. It's the negative of the potential energy, not the actual potential energy. Right? So I've always been miffed by this, and my way of addressing this is to say, hey, I'm not in a physics class. Right now, I'm not in a physics department. And my applications are not uniquely to physics, right? So I'm going to use the term antigradient. I think it's much more natural. It's universal. Doesn't matter what field you're talking about. That's field of study, not vector field, right? So I like the term antigradient. Outside of my class, you're going to probably more likely hear the term potential function more often, and you just have to remember, okay, don't forget the minus sign, and you're going to have a minus sign confusion. That'll haunt you as you do that. Okay, we doing okay? All right. Okay, so why are we talking about vector fields? Who cares? What does this have to do with the real world? Or is this just a made-up mathematical construction to let mathematicians have fun? And it's extremely applicable. It's extremely relevant in the real world. And just to kind of get the ball rolling here, I mean, in three-dimensional space, let me get out of the red. That's unpleasant. There we go, green. In three-dimensional space, here are some examples of things that we model with vector fields. How air flows. Right, so let's take in this room. Right, I can hear the air conditioner going. Right, so I think those are where the air comes in, and no, that's where the air comes in, and maybe those are where the air comes out. Right, which means that if you were to pick some point, like here, maybe let's look at this point right there. The air might be flowing, not much, but maybe a little bit. Let's say kind of that way, or something. So at any given point, we can talk about the velocity of the air, and therefore at any point there's an associated vector. That's what I need to represent. If I want to talk about the velocity of the air in the room, it's exactly a vector field. At every point there's a vector. Is that cool? Everybody see that? Okay. So likewise, with some other examples here, you can talk about ocean currents. In any given location, and its corresponding velocity of the water. So, same deal. You can talk about how pollution flows around, right? And that might not be the same as the velocity of the air itself, right? You don't have to have actual wind right, for pollution to kind of just dissipate, right? And you could talk about how is the pollution moving, vector field. And likewise, any other thing, what I'm going to call here atmospheric components, if you want to keep track of how the ozone is moving around inside the atmosphere or what have you, then also, again, vector fields. So these are kind of maybe a little bit more relatable as vector fields because we live in a three-dimensional world. We're three-dimensional people. We understand three-dimensional things. I'm going to point out, though, you can also see real-world examples in 2 dimensions. So animal migrations is my favorite. I mean, animals aren't, we don't think of them as being a fluid exactly, but I'm gonna point out they kind of are. This is a weird thought, all right? But a lot of people say no. A fluid is like it's like water. Water is a fluid, classical fluid. What's water made up out of? Little bitty elemental kind of little particles called molecules. It's a bunch of particles. Right? So if I have a herd of wildebeests, that's a bunch of little, if you're looking at a movement of, you got 1 million wildebeests, right? And they're doing whatever they do. From a satellite, you look down on it and it's like, wow, there's this kind of fluid flowing across the land. It's kind of like a fluid in a way. Does that make sense? And so vector field, a vector field on the surface, right, is what represents that motion. And likewise, you could imagine a similar argument. How does surface water flow, right? Again, kind of a fluid. Okay. All right. So tons and tons of applications. I'm going to show y'all an example of a certain calculation. This is I'm going to say very important. This is a motivating example. This is an example that motivates a particular quantity that we're going to study at great length in chapters 6 and 7. And again, when we get there, so it's also kind of getting ahead of ourselves. Supposing that we have a vector field representing the flow of a fluid. Specifically, suppose that the field vector represents velocity. That's a very common choice, right? Because if you think about it, again, if you have fluid flowing at any given point, you might want to talk about just how fast the fluid is going there. Okay, in which direction? Okay, so I want to talk about the flow rate. How much quantity of fluid per unit time is moving through some surface, something like that. Now, I distinguish between velocity, which says distance per unit time in a direction, versus flow rate, which you'll notice is volume of fluid per unit time. Right? They're not the same thing. Right? Furthermore, to talk about a flow rate, I have to say flow rate through what? And so presuming that we have some area down here, right? I can ask how much fluid per unit time is flowing through that area. So an example, maybe this is a screen door, right? And the wind's blowing. Well, how much air is actually getting into the house through that screen, for example? Does that make sense to everybody? Here's another example. Maybe you have a net out in the ocean, right? And you've just got a net down there and you're catching fish and you're holding the net in place, but the ocean current is making the water flow through that net. Well, the more water flows through the net, the more fish you catch, right? Again, kind of plausible, I think. Okay. All right. So the calculation here is actually pretty straightforward. If you have your vector field is representing velocity, again, keep in mind, vector field represents velocity. So that's the velocity of the fluid, right? Then I can talk about how much fluid per unit time. Let's see, I'm going to do this with an arrow, with a pencil. I can talk about the displacement in a given amount of time, some little small amount of time dt. This is how much the fluid actually moved in some amount of time dt. Which, of course, is the same everywhere if we have a constant vector field, so all of these are the same d. Right? Okay, so let's talk about the volume. The volume we're interested in. That volume is going to be the area in question times this height. Right? Now, again, an old high school formula, right? Height times area gives you volume. And then just a couple of games to notice. The height, you'll notice, is the normal component of the displacement vector d. And let's see here. Now I'm making a mess. So height is that component there. That's the component in the direction of a unit vector, which means it's just a dot product, right? And then let's see here. That displacement vector is velocity times time. And keep in mind, that's what the field vector is the velocity. So displacement equals velocity times time gives me that. And so the punch line with all of this together is that, if you will, let's see, for highlighting purposes, volume per unit, color choices, volume per unit time is this thing right here, F dot N times area. So that's the flow rate is F dot N times area. It turns out that this expression, F dot N times area, is a really interesting quantity called flux that we're going to do, again, tons of stuff with when we get into 6 and 7. Y'all have a good day. See you later. Don't forget to stick around if I didn't get you marked down for attendance.